Hello students, welcome back. Previously we went through a couple of problems associated to Fermat's theorem. We went through this, mod 13, and then this one, mod 11. Both are prime numbers, 13 and 11, so we could use this one. Now let's do part C. This time it looks like it is a job for Fermat-Euler extension, because 15 is a composite number. Okay, how do we handle that? Well, all right. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, from here, which one is congruent, which one is relatively prime to 15? This is okay. And then that's okay. And 3, no. And that's okay. 5 and 6, no, they are not relatively prime. The 7 and 8, 9 and 10, no. And 11, yes. 12, no. And 13 and 14, yes. So did I highlight the whole numbers less than 15 that are relatively prime to 15? How many are there? 1, 2, 3, 4, 5, 6, 7, 8. Okay. Phi of 15 is 8. So it looks like we have n to the 8th power is congruent to 1 according to Euler-Fermat theorem. Okay, all right. N to the 33rd power, you can rewrite it n to the 32nd power plus 1. And then that's n to the 8th power to the 4th power. That's 32, right? 8 times 4 times n to the first power. First power, I don't have to write it. So that's just n. So looks like I'm getting this. N to the 33rd power minus n is congruent to n minus n, 0, mod 15. All good? No, there's a problem, and find out something is not right. Find out, please. Did you find the imperfection? What did I do wrong? By the way, the answer is 0. I got correct answer. It's just that I didn't cover everything that is possible. Why? This one here, the GCD of n and 15 is 1. I used to use blue, so let's keep blue. So if GCD of n and 15 is 1, so this is missing. And that's not always true. Now we want to do it for arbitrary n, and we did it only for these. Or these numbers highlighted in, maybe I should have highlighted in blue. So other cases, when n is 3 or 5 or 6 or those kind of numbers, then how would it work? So this proof is not perfect. Here we go. Incomplete solution number 2. That's what I showed you just now. We got that, and then looked like we got 0. What's missing? Another way to do the same thing is to use Fermat's original theorem written for prime numbers. In this case, we have this condition here. So n to the 32nd power times n and the 4th power to the 8th power mod 5, or n to the 32 power to the 6th power, and to the 2nd power is 1 mod 3. So either way, I used Fermat's theorem, this one here. And then, well, let's see, both are congruent to n, modulo 5 and modulo 3, and the LCM is 15, so mod 15, it should be the same as well. But what's missing? The same thing here. Not the same thing, the similar thing here. If A is not a multiple of P, it works out. In this case, if n is not a multiple of 5, and also n is not a multiple of 3, either way, either one or the other. So if n is not a multiple of 15, it'll work out, but otherwise we have a problem. So how to get it right? Well, one way to get it right is to use this one down here. That always works. So a to the p power is congruent to a. So step 1, a to the 33rd power, 32nd power times n. Works out. Now if 5 divides n to the 33rd power directly, either way we have n. Step 2, if 3 does not divide n, same as before. If 3 divides n, a special case, 0 to the 33rd power. So either way it works out. So either way, we get 0. It's true, but this solution method is not general enough. It worked out this time, dividing case 1, case 2, and then case 3, case 4. Many times this is going to be too complicated and you may leave something out. It's going to be better to use this one here. So the final solution here, solution 2, is the one that I'd like to emphasize, and this one always works. A bit cumbersome, yes, but it always works. Basically what I want is a to the p power is congruent to a, mod p. Okay, for mod 5, a to the 33rd power, and then work out. A to the 30th power is n to the 5th power, and that's brings down to n. So that's bring down to just n. Purple and that purple. Alright, now we have 6th power. We got down further. And then let's see. 6 plus 3 is 9. Again, we could do 5 plus 4 is 9. So this one here becomes just n. And then we have 5th power, that brings down to n. So n to the 3rd power is congruent to n, mod 5. How about mod 3? We do the same thing. 3rd power is congruent to 1, so we're down to 11th power. and then 9 times 2 so that we get third power to something. Again, third power is congruent to 1, just 1 power, so just n. And the third power is congruent to just n. So we are using this. Third power going down to 1 power. Previously, fifth power going down to its first power. That's how you can reduce the power, and eventually you come down to n. So either way, n to the 33rd power is congruent to n. It is a systematic method, and it works out using this one here. Want to do one more exercise? Okay, all right. Here we go. N to the 7th power minus n. So if I give you a hint, n to the 7th power is congruent to something mod 7. Okay, all right. And then mod 3 mod 2. That's what you want to do, because 42 can be decomposed as 7 times 3 times 2. Try on your own. Well, did you get something? Well, time's up. Alright, that's mod 7 computation. Mod 7 is congruent to n. Mod 7 has come down to n. Let's see, is that the solution? Yeah, okay. Sorry, this is the solution that I want to emphasize. N to the 7th power is congruent to n mod 7. Okay, all right. Directly, a to the p power is congruent to a. So, okay, we got that. And then mod 3, 7th power, bring out to 6 power times n so that we get a third power. But third power go down to just the first power n. So enter second power, third power again, and going back to n. Next, enter 7th power, second power to the third power, but second power is going down to just n. And then this is third power and then 1, so total fourth power, so n squared. And that thing here is again coming down to n. And then n squared is coming down to n again. So eventually, you're going to get n in all three cases. So n to the 7th power is congruent to n. So n to the 7th power minus n is congruent to 0, modulo 42. And then, of course, the second solution is you can divide as case 1, case 2, case 3, case 4, case 5, case 6. You can do all those, but I do not recommend those. It works out, yeah, but too many cases, you may end up losing things out. So prepare to use this for a little bit tougher problem, because it works every single time. But if you're just looking for an answer, just do this or do that to find out the answer. And then we can consider singular cases later and refine those with these. Anyway, that's how you can apply Fermat's theorem. And now I guess we'll do the proof of Fermat's theorem and Euler's extension in the next video, of course.